Today, we're going to start talking about virtual memory, one of the most useful things that we can do with our paged memory hardware. You already know about the storage hierarchy or the memory hierarchy. You know that on a computer system, we've got many regions of storage, but they're usually, they vary both in terms of performance characteristics and size. And like I started to say, they're usually organized from the smallest, fastest regions of storage, which can just hold a little bit, up to larger, typically slower regions of storage. We've been trying to figure out how to get the most out of a limited physical memory. On a modern computer, main memory might be in the neighborhood of 4 to 16 gigabytes of storage. But we always try to think of that as being not quite as much as we'd like. We're always trying to figure out clever ways to fit more or larger processes in that limited physical memory. So what if our main memory isn't enough? Well, it's not our bottom level of the storage hierarchy. We've got bigger, slower storage areas, typically in the form of secondary storage, like a magnetic disk. Could we use that to extend main memory? Kind of using the same tricks we've used across the entire hierarchy, keeping just the parts we need of running programs in main memory and keeping the rest on secondary storage and just bringing them in when we need them. We've already got a mechanism for doing this. We talked about it in the last chapter. In fact, we didn't even need paged memory hardware to do swapping. That was the idea that if physical memory got scarce, we could pick a program that maybe wasn't particularly busy. We could block it for a long time and take its memory and write it out to secondary storage with the idea that we can bring it back in later and let it resume executing when memory is less scarce. But with paged memory hardware, we can do this same trick, but just a little bit of memory at a time rather than swapping out whole processes. Maybe we can bring just page-sized pieces of a process in and out of secondary storage. And that's the idea behind virtual memory. We'll extend our memory hierarchy to include parts of secondary storage, so parts of running programs, page-sized pieces can reside on secondary storage, and maybe only a little bit of some running processes needs to take up space in main physical memory. This is a picture out of your book showing how you can think about this. The picture on the left is sort of how a process views its memory. It still can think of it just as a bunch of pages, maybe even contiguous pages in memory. But some of those pages we're going to keep on disk, some of them we'll keep in main memory, and we'll need a data structure, maybe with a lot of help from the existing page table, to figure out what parts are in memory or to keep up with what parts are in main memory and what parts are out on secondary storage right now. So the idea here is we can keep the most frequently used stuff of a process, the most frequently used pages, we can keep that in main memory. And the stuff it's not using as much, the less frequently used pages, we'll keep on secondary storage. And then whenever a process tries to access one of those pages that's on secondary storage, we're going to have to go get it and bring it into memory so that the process can access it. And that's really the idea behind demand paging. We'll bring pages in when processes show that they need them by trying to access something on that page. Now we're going to have to figure out how we make this work. If we're the operating system, how do we know when a process needs to access one of its pages? When it does, we'll need to, like I said, we'll need to go get that page off of secondary storage and bring it into main memory. We've got a word for that. We call that paging in the page. And once memory gets full, we're eventually going to have to start taking pages out of memory and putting them back on secondary storage to make room for others, and we'll call that paging out. Whenever a process tries to access a page, we'll have to page it in, or at least if it's not memory resident. And memory resident just means it resides in a frame of physical memory. If it's not memory resident, the OS is going to have to page in that page. So again, the idea of demand paging is we'll page in stuff whenever processes try to access it. Pure demand paging is kind of the extreme form of this. It's the idea that we'll only bring stuff from secondary storage into main memory when a process tries to use it. This could save us some I/O, especially at process startup. Maybe there are big parts of the process's code or its load image that it rarely actually uses. We might never have to bring those in. So we get more available physical memory if not all processes are using all parts of their code, or if they don't all actually need it in main memory. And this would let us fit more processes in a limited physical memory. So continuing to try to get as much as we can out of our physical memory. So we sort of skipped a critical idea on the previous slide. I said, well, as processes are running, some of their pages will live in memory frames, and for those pages, their page table will let them access those pages just like they normally would. But some of their pages won't be in physical memory frames at all. They'll be out on secondary storage. And I said, whenever the process tries to access it, that's when the OS has to go in and page in that page. But how does the OS know when a process wants to access a page that isn't even in memory? Well, there's a trick we can do to at least figure this out as the OS. We'll just take all of the pages that aren't memory resident, the ones that that live on secondary storage right now, that don't actually live in a frame of physical memory, and we'll mark them as invalid in the page table. What will that do? Well, remember, if a page is marked as invalid in the page table, then if a process tries to access it, the hardware automatically traps to the OS. So that's going to be our mechanism for figuring out when a process wants to access a page. Again, we'll mark it as invalid, and then if the process tries to access it, the OS will find out about that right away, because the hardware will think the process is trying to do something sneaky, trying to access a page that is invalid. And then the hardware will trap to the OS, and then the OS can decide what to do. And that's what I'm trying to say on this part of my slide. Now, whenever a page fault occurs, whenever a process tries to access a page that's invalid, the OS has really two situations to worry about. Maybe the process is trying to access memory that isn't even its memory at all. That'd be just like trying to access an array out of bounds, or trying to access memory that wasn't part of your process. That's still a bad thing. If processes try to do that, the OS is probably going to terminate the process and say something like segmentation fault. But now we have to worry about the idea that a process could access an invalid page, and maybe that's a page that the process should have. It just doesn't happen to be memory resident right now. In that case, if the OS can determine, oh, you're trying to access a page that you should have, I've just got it on disk instead of main memory, then instead of killing the process, the OS is going to service that page fault. It's going to go get it off disk and bring it into main memory. Here's a picture out of your book that's showing the same thing I was just talking about. If you're a process, you might think of all of your pages as being one after another in memory, but in reality, maybe only a few of them reside in frames of physical memory. So this picture shows maybe just 3 of them are in physical memory. If we looked at your page table, all the ones that are in a frame of physical memory, they're marked as valid, and the process can access those right away if it wants to. But if it tries to access page B, well, that's not in its page table, or it's not in a frame of physical memory. Its page table has that one marked as invalid. It's really out there on disk, it's just not memory resident right now. So if the process tries to access that, the OS is going to have to go get it off disk and find room for it in memory. What's it take to do that? Well, this is sort of a to-do list for the operating system for what to do or what's going to happen when a page fault happens. And it's a lot of what we were just talking about, maybe with just some more details added in. So for demand paging to work, here's sort of how it will go whenever a process tries to access a page that's not memory resident. So if it tries to access a page that's out on disk instead of in memory, that'll look like accessing an invalid page. The hardware will trap to the OS, and it'll automatically switch us into kernel mode, just like we would for any trap. Inside the operating system, we got to decide what to do. If that's a page the process shouldn't have in the first place, we will complain, we'll kill the process, maybe we'll send it a signal depending upon what OS you're running on. But otherwise, if that's just a page, so we're down here at number 3, otherwise, if that's just a page that's out on disk, and we'll call, we started doing this in chapter 1 of the book, but I'll just remind you, we'll call that region of disk where we're keeping pages of a process that aren't memory resident right now, we'll call that backing store. So we can kind of think of main memory as holding a subset of the pages that are out there on backing store. All right, so like I was saying, if the page is out there on backing store, the OS is going to have to find a place to bring it into, so an available frame to bring it into. It's going to have to block process P because until we've brought it into memory, that process can't access the next thing it wanted to do. So we'll mark it as blocked, and we'll schedule I/O to bring that page in. And this is really, it's a lot like any other I/O. It's going to take a while for the I/O to complete. It's kind of like I/O that the process didn't really ask for. It was just trying to access some of its own memory. But when it did, the OS had to do I/O. It had to schedule a page in operation to give the process the access to the page it needed. So this I/O operation is going to take a while. Just like any other I/O operation, the OS is going to figure out something to do with the processor while this is happening. Typically, if there's another process that wants to run, and the guy that just page faulted is blocked at least for a little while we page in the thing it was trying to access, then we'll let some other process run for a little while, and then sort of continuing at item 5, even if the OS is letting some other process run for a while, eventually the I/O to bring in that page will complete. Just like any other I/O, it'll interrupt the CPU. That'll give the OS another chance to run. It'll figure out, oh, that was the page fault that I had scheduled a page in operation for. This process should be runnable now, so let me get it ready to resume executing. That's going to mean fixing up its page table. Previously, the line that it just page faulted on was marked as invalid, but now that that page is memory resident, we can mark it as invalid, and then we can let the process resume running. That'll usually mean marking it as runnable, and then maybe putting it back on the ready queue. And when it resumes running, it'll rerun the same instruction. Maybe it's got an instruction that when it was trying to execute that instruction, it page faulted. We'll give it another chance to rerun that same machine instruction. So here I tried to number all of these steps, and I tried to do it in a way that matched this figure. We won't go through this again because it would be repeating a lot of the same stuff we just said, but this sort of shows the sequence of operations we just talked about. A process page faulting, scheduling I/O to bring in its fault, to page in its faulted page, patching up the page table, and then letting it resume running. If we back up partway through this, we said when a page fault occurs, you got to bring in the faulted page and you've got to find an empty space to put it in. And that's great if there are some available frames, but like I suggested a moment ago, eventually, if you're running a lot of processes, you're probably going to fill up all the frames in your physical memory, and you're not going to have any empty frames to bring faulted pages into. What this means is whenever a page fault occurs, it's usually not just a problem of bringing in the page that some process was trying to access, but we've got to pick some page to throw out of memory to make room for that. And we'll call that a victim page. Again, if memory's full, every time a page fault occurs, you might be having to pick a victim page to take out of memory, to write back to backing store, just to make room for the page that faulted in. And I think this shows that a page fault can be really, really expensive because it's not just a matter of the I/O to bring in one page, it also includes typically I/O to write out some other page, plus a bunch of other little operations to do things like clean up the page or patch up the page table after a page fault is done. So this means that if processes are page faulting occasionally as they run, they're going to run a little bit slower. We can figure out how much slower, or really what the overhead cost is for page memory by computing really an average effective memory access time for accessing memory when page faults are happening occasionally, every so often. To be able to do this, we'd have to know or make up some run times. We'd have to make up some parameters for this problem. So that's what I've started to do here. So if we wanted to compute the effective memory access time, so on average, what does it cost to access memory, given that usually it's pretty quick to access memory, but occasionally we've got to pay to service a page fault. Well, the first thing I'd want to know is how often do page faults occur? We'll call that the page fault rate, and we can pretend that's some number p between 0 and 1. So if it's close to 0, that means page faults are almost never happening. If it's close to 1, that means page faults are very frequent. And then the effective memory access time would just be the weighted average between, well, when you don't page fault, what does it cost to access memory? So that would be, when you don't page fault, would be 1 minus p times whatever it costs to access memory without a page fault. And then everything else, p times what it costs to access memory when you have to service a page fault before you can access it. And for this part, I just added up most of the things we talked about on the previous slide. We already said when a page fault occurs, the hardware has to notice that a process accessed an invalid page and trapped to the OS. The OS has to figure out, oh, that was a page that was on secondary storage, and schedule I/O to bring it in. That might include paging out a victim page, if memory's full, and I/O to page in the faulted page. And then we said plus some overhead to fix up the page table, and then finally let the process access the memory it was trying to access in the first time. I made up some numbers for these, so let's pretend that accessing main memory costs 200 nanoseconds. That's pessimistic. Realistically, if you had some cache helping out, you'd expect to do much better than that, but that was a nice round number. And let's pretend servicing a page fault, all those costs together cost about 8 milliseconds. That's typical of I/O operations to try to access a magnetic disk, so hopefully that's not too far off. And let's pretend your page fault rate is infrequent. I just made up a value p here of 0.1%. So that means 99.9% of the time you're not page faulting, and you're only page faulting, again, 1/10 of the time. Sorry, 1/10% of the time. So if we add up these as a weighted sum, same thing on the previous slide, that'd be almost all the time you pay 200 nanoseconds. Only 0.1% of the time you pay this larger 8 milliseconds cost. And 8 milliseconds doesn't sound that bad until you express it in nanoseconds. That's 8 million nanoseconds. And that cost is so big that even with this tiny page fault rate, it still gives you an average effective access time of 8,200 nanoseconds, which is 41 times slower than if you didn't page fault. So this shows even with what seems like a small page fault rate of 0.1%, that's still a unacceptable amount of overhead. It kind of tells us to get acceptable performance from our memory, or from our virtual memory system, we need page fault rates that are way lower than that. Otherwise, the significant cost of servicing a page fault is going to dominate the typical cost of accessing memory. So the takeaway here is we can compute effective memory access time as long as we know what the page fault rate is and what the cost for accessing memory and servicing a page fault are. And if you're the OS, you should do whatever you can to try to achieve a low page fault rate to help processes run efficiently. If you're the OS, what can you do to achieve a low page fault rate? Well, unfortunately, a lot of this is in the hands of the processes. They kind of know the pattern that they're going to use for accessing memory. They know how much memory they're going to need. For the OS, it seems like there are two things you can do. You get to decide how much memory to allocate processes. Processes that need to use a lot of pages, you might have to give them more frames, and ones that don't need to use as many pages, you could give them fewer. And then the other thing, really the main thing we're going to talk about, is you do at least get to choose the victim. Remember, when a page fault occurs, if memory is full, we might have to throw out a page to make room for the new one, and we call that the victim page. The OS gets to decide what to throw out. Choosing a good victim can help keep the page fault rate low. When we're picking a victim, I guess we want to pick a page that nobody's using anymore. I say that because it seems like the worst thing to pick would be a page that a process is using heavily, or that lots of processes are using, because if we throw it out of memory to make room for another page, we're probably just going to have to bring it right back into memory later. So we need a good way of trying to decide what pages make good victims. We can't deliberate about this too long. As the OS, we got to make a quick-ish decision, but if we make a bad decision, we're probably just going to end up reversing that decision later on. There is one other choice the OS can make, and this is really in how it allocates frames and how it chooses victims. The OS can enforce either a local or a global page replacement policy. And that just means, I guess a local policy means when a process page faults, one of its pages will be chosen as a victim. So you can effectively steal pages, but only from yourself. Whenever you bring in a page, you got to throw out one of, or the OS will choose one of your pages to throw out. Versus global, which says when a process page faults, anyone's page could be chosen as a victim. So if you page fault and some other process has a page it's not using very much, its page, a different process's page, might get chosen as a victim. So choosing a victim page, like I tried to say, it's one of the most important things the OS can do to try to keep the page fault rate low. And we've got a name for that. Sorry, I messed up the slides there. The policy that the OS uses to choose a victim is called its page replacement algorithm. And it's really just the policy of which victim you select. We are going to talk about, kind of like we did for CPU scheduling, we're going to talk about a few different basic policies you can use for picking a victim. We'll talk about some fairly simple algorithms and what we could try to do with those algorithms. And we'll try to work up our way to the kinds of algorithms that show up in realistic operating systems. We'll do this, at least we'll look at what these algorithms do, kind of like we did with CPU scheduling. We'll make up some tiny little page replacement problems, and we'll work them out and see how various algorithms do. Kind of asking questions like, if we did page replacement this particular way, how many page faults would we get? Would it perform well or would it perform poorly? One thing we expect, this is a chart out of your operating system, one thing we'd normally expect is if we give a process more frames, it's not going to page fault as much. That makes sense. That's what this chart is trying to show. Here on the x-axis, we're showing how many, we're pretending we give a process different number of frames. So if you gave it 2 frames, what would happen? If you gave it 5 frames, what would happen? Vertically, we're showing kind of a made-up curve for what we might expect. If I give you just 2 frames, you're probably going to have several page faults. If I give you a little bit more memory, you're probably not going to page fault as much. And again, I think that makes a lot of sense. If you've got more space to work with, you can keep more of the stuff you're actually using in that space, and the process won't page fault as much. So like I said, we'll go through a few different basic algorithms for doing page replacement. We'll start with the simplest one. First in, first out. First in, first out just says whenever a page fault happens, you're going to pick as a victim the page that's been in memory longest. The nice thing about this, and we'll talk about this a little bit later, is it's really computationally cheap to implement. If all I need to do is know which page has been in memory longest, I can just keep up with that, and then when I pick it as a victim, the guy who's been in memory second second longest is going to be my next victim after that. So like we'll see, we can really do this with just keeping a pointer to the next page that's going to be chosen as a victim. We're going to try simulating first in, first out on a tiny little made-up problem. I've got another little video that I'm going to insert in just a moment that shows kind of trying to work this out, but let me try to explain it first. So to simulate these, we'll pretend we have a reference string. That's just the idea of pretending the process is going to access pages of memory in a particular order. For a real problem, we could even extract this by watching a running process and watching what pages it accessed. Here we just made up these reference strings. So here I'm pretending it accessed something on page 1, then it wanted something on page 2, then it wanted something on page 3, and so on. And as the process tries to access stuff on its pages, we'll watch what the OS would do as it brings those pages into frames of memory, lets the process access them, and then eventually has to start throwing stuff out of memory to make room for new stuff that the process tries to access. So here, let's work out a simple example that tries to show this. So let's try out first in, first out on a really small example to see how it does. Here I've got a picture to show what we're going to try to simulate. Up here at the top, we're going to pretend this is the reference string that some process is going to access. So first it wants something on page 1, then it wants something on page 2, and then 3, and so on. Down here I'm pretending I've got 3 frames of memory to work with. That's way smaller than you'd really expect to have for a real process, but it's small enough that it's not too hard for us to simulate. You can see up here the process is accessing 5 different pages, so they're not all going to fit in memory at once. Initially we're assuming those frames are empty, so we can bring in pages, we can page them in as the process accesses them. But pretty soon we're going to run out of frames of memory and we're going to have to start throwing out pages to make room for new pages that get referenced. So in these little boxes, I'll try to show what the process is, what's being brought into memory. I'll also try and keep a count of the total number of page faults that happen so that we can see how first in, first out does on this reference string. All right, so let's give it a try. First, the process accesses page 1. That's not in memory, so we'll bring it into the first frame here. And we had to page something in, so we'll charge a page fault for that. And I'll keep a little count of the page faults over here. Then it accesses page 2. That's not in memory, so we'll bring it into the next available frame. Then it accesses page 3. We'll bring that, oops, I should have counted a page fault for accessing 2. Then we bring in page 3 into the next frame, and that cost us a page fault. And now we filled up all of our frames, so any new pages we access from this point, we're probably going to have to throw out a page. So when the process accesses page 4 right there, we have to make room for it. So we're going to throw out, like first in, first out does, we're going to throw out the page that's been in memory longest. And since we filled up the frames starting at the start and working our way down, it must be this frame, or it must be this page 1 in the first frame. So I'll pretend it gets thrown out of memory, and then I'll bring in 4 to take its place, and that was another page fault. Then we access page 1. That's not in memory. Who's been in memory longest? Well, since I filled up the frames starting from the start, the next guy must be 2 here. So I'll throw that out. And I'll bring in page 1 to take its place. And then when I access page 2 next, I'm going to throw out 3 to make room for page 2. And I think I forgot to count those last 2 page faults. So when I brought in page 1, that was a page fault. And when I just brought in page 2, that was also a page fault. So notice the nice thing about first in, first out is it's easy to keep up with who the next victim is going to be, what page you're going to throw out to make room for another. We filled in the frames top to bottom, and then when we had to pick a victim, we went through the frames in the same order, throwing out pages. And the same thing's going to continue to happen. So when we have another page fault, it's going to be 4 that gets thrown out because it's the one that's been in memory the longest. So when we reference 5 over here, we're going to throw out 4 to make room for 5. And that's a page fault. And then finally, or at least at this point, we get a little break because when we reference page 1, it's already in memory, so that's not a page fault. When we reference 2, it's already in memory, so that's not a page fault. But when we reference 3, it's not in memory. At this point, page 1 is the next victim, so we'll throw it out to make room for 3. And that was a page fault. And then when we reference 4, it's not in memory, so 2 is going to be our next victim. It's the one that's been in memory the longest at this point, so we throw out 2 to make room for 4. And then lastly, we access page 5. It is in memory. Oops, I didn't count page 4 as a page fault. All right, so where was I? 5 is already in memory, so it doesn't count as a page fault. So we end up with a total of 9 page faults for this reference string, provided we have 3 frames. So here we're going to try the same reference string as before, but we're going to give the process a little more space to work with. Here we're pretending it has 4 frames, and we normally expect the process to do better. If you've got a little bit of extra memory to work with, you can keep in memory more of the stuff you're actually using. Let's give it a try and see what happens. We're still using FIFO, so the start of the reference string is easy. It references page 1, that's not in memory, so we'll bring that in. It references page 2, we'll bring that into the next frame. It references page 3, we'll bring that into the next frame. And then 4 goes into the next frame. And that was 4 page faults. I didn't keep a tally of them, because I'll show you another way to keep up with that that's actually a lot easier. If you remember from the previous example, I sometimes forgot to make a tally mark and had to go back and add that in later. This sort of keeps up with it for you, at least for most page replacement algorithms. This works pretty well. So we've accessed the first 4 pages in the reference string, and each of those cost us a page fault. But now, when we reference page 1, it's already in memory, so we don't have to bring it in. When we reference page 2, it's already in memory, so we don't have to bring it in. But then when we access page 5, we're going to have to throw out really the one that's been in the longest, so that's 1. But instead of erasing it, I'm just going to make a little mark through it, and I'll put 5 right out here next to it. And the nice thing about that is, if every time I bring in a new page, or every time I have a page fault, I mark out the old page that was there and write down the new page right next to it, that sort of keeps up with the page faults for me. I don't have to keep a separate tally off to the side. When I'm done, I can just count up the total number of pages I had to bring in memory at some point, and that'll automatically keep up with the page faults for me. So far, we've had 5 page faults, and we're all the way up to this first 5 in the reference string. But now things are not going to go as well, because when we access page 1, it's not in memory, so we're going to throw out the guy who's been in the longest, which is now page 2, to bring in page 1. When we access page 2, we're going to have to throw out page 3 to bring in 2. And we're feeling kind of stupid because 3 was the one we were going to access next. We just didn't know that. The algorithm didn't have any way of knowing that. So when we access page 3, we have to throw out page 4 to bring in 3. This is another nice thing about scratching out the old pages like this for a simple algorithm like FIFO that also keeps up with who the next victim is going to be. You just keep going through the frames, top to bottom, over and over again. So now when page 4 gets referenced, we're going to throw out 5 to bring in 4. And when page 5 gets referenced, we're going to throw out 1 to bring in 5. So that's what should happen with 4 frames of memory using the same reference string. But we see something disappointing here. If we count up our number of page faults, there were 4 there and 4 more and then 2 more. So that's a total of 10 page faults, which is worse than we had with just 3 frames. With 3 frames, you remember we had a total of 9 page faults, and here, at least with this particular reference string, going from 3 frames to 4 frames actually gives us worse performance. We pay for extra page faults. All right, so we just did a couple of simulations to see what our simplest page replacement algorithm, what FIFO would do, and we saw maybe an unexpected result. I had planned for it, but I tried to make it seem unexpected, and that is that normally we expected that when you give a process more frames of memory, it's going to have fewer page faults. It can keep more of the stuff that it needs, in memory at once. And often that's going to be the case. I would say usually our intuition is right on that, but we just saw that that's not always the case, and we're not the first person to see this. This is called Belotti's anomaly. In page memory, it shows that in some cases having more frames can actually make your process do worse. This had to be a carefully constructed reference string to make this happen, but this is certainly not the only reference string that could make it happen. There are any number of sort of memory reference patterns that might make it so you actually do worse with a little bit more memory. A thing to remember is this doesn't just happen in page memory, or in virtual memory. This can happen at any level of the memory hierarchy. In special cases, having more cache space might actually make your process run a little bit slower if the hardware doesn't do as good of a job as at deciding what to keep in memory. So Belotti's anomaly is the fact that having more memory, having more frames, can actually make you do worse. Not all page replacement algorithms exhibit Belotti's anomaly. There's a name, stack algorithms, for a particular kind of algorithm, and a nice thing about it is stack algorithms are guaranteed to never exhibit this anomaly. To describe what a stack algorithm is, I think it's a simple idea. It's just a little bit hard to say. So I've tried to say it two different ways on this slide. Informally, it's the idea that if I give you a little bit more memory, you'll always be keeping the same stuff in memory, maybe with just some additional stuff. So the first way I tried to say this is, if I give you some number of frames f, and then I watch what pages you keep in memory, at any point, the pages you have in memory would always be a subset of what you would have kept if I gave you an extra frame. So having an extra frame will always let you keep everything you would have kept with fewer frames, maybe typically with some more stuff in memory. The second way I'm trying to say, the top way is probably the more formal definition, and the second way I'm trying to say it is probably the more informal, but maybe the easier to think about. If I give you more frames, it'll let you keep some additional stuff in memory, but you always keep the stuff that you would have had in memory with fewer frames. So if we can identify algorithms that are stack algorithms, I guess we would at least, we'd be confident that they're not going to exhibit Belotti's anomaly. Having more memory will help them do better. It won't let them do worse. I guess a takeaway from this is FIFO is not a stack algorithm. It's not guaranteed to improve performance with more memory. What's nice about it? Well, it's fast. I already said a nice thing about it is it's easy to implement, and the OS can make quick decisions about who's going to be the next victim. The problem is it just doesn't always make good decisions about who the victim is. It might pick victims that are heavily used by the process. I guess worst case, it might pick a page as a victim that the process is about to use right afterward. And you don't want to throw out something that the process is going to need again right away. Well, that, I think, could give us an idea for what a really good victim would be, and that is, if you're trying to pick a victim, why not try to pick the page that won't be used for the longest time in the future? If it's a bad idea to pick a page that's about to be used maybe in the next CPU instruction, why not pick instead, why not pick a page that won't be used for a long time in the future? And we're not the first people to think of this. In fact, the algorithm for doing this is called the optimal algorithm. We'll just call it the optimal page replacement algorithm, or we'll abbreviate as opt. And it's called that because it is guaranteed to give you the fewest page faults for any reference string. I made up an example to show this. Really, it's the same example we had before. We'll pretend, just like with FIFO, we'll pretend we have 4 frames, same reference string. Let's see what happens. So here, we're going to try out the optimal page replacement algorithm in the same situation as we were doing with first in, first out a moment ago. We're same reference string here, and we're assuming we have 4 frames of memory available. So if this algorithm's really optimal, it should do at least as well as FIFO. And remember, FIFO got 10 page faults on this reference string, so we better do at least that well. In fact, FIFO got 9 using only 3 frames. So if opt is really optimal, it ought to do at least as well as 9. Let's give it a try and see how it does. We'll do the same trick we did before. We'll mark down pages as they get paged in, and then when they get replaced with some other page, we'll mark through them and write the other page down next to them. So it starts out simple enough. We're assuming we don't have anything in memory initially, so all of our frames are empty. So when the process references page 1, that we'll assume gets brought into the first frame, and then page 2 gets brought into the second frame, and page 3 gets brought into the next frame, and then page 4. And that's 4 page faults right there. But we couldn't have done anything to avoid that. The process wanted all of those pages. And then when it references page 1 here, that's already in memory, so we don't have to do anything. When it references page 2, that's already in memory, so we don't have to do anything. When it references page 5, we're going to have to throw something out of memory. For opt, it always makes the decision to throw out the page that it won't need for the longest amount of time in the future. So looking ahead in the reference string, we better not throw out page 1, because we're going to need it right afterward. We better not throw out page 2, because we're going to need it right after that. We better not throw out page 3, because we're going to need it right after that. So if we had to pick a victim, we're going to need 4 later, but that's the longest time in the future. So let's throw out page 4 to bring in page 5, and that cost us a page fault. But now when we we just referenced page 5, that did cost us a page fault, but fortunately we didn't throw out page 1, so it's still in memory. That's not a page fault. Page 2 is still in memory. Page 3 is still in memory. And then we finally reference page 4. We have to throw out something to make room for that. Looking ahead in the reference string, we better not throw out page 5 because we're going to need it right away afterward. And then there's nothing that gets referenced after that. So among the other 3, page 1, 2, or 3, it doesn't matter which one we throw out. They're all going to perform just as well. We just better not throw out page 5. So we'll pretend we throw out the first one, page 1, to make room for page 4. That cost us a page fault. But now when we reference the last page, 5 is still in memory, so that's not a page fault. We're done with the reference string. We can count up our page faults just by looking at how many of these things we wrote down. And yeah, we got 4, 5, 6 page faults, so 6. So much better than FIFO did on this same reference string. Remember, with 4 frames, it got 10 page faults, and even when it only had 3 frames, it got 9. So we are doing a lot better in this case. So we've done a few simulations of basic page replacement algorithms using made-up reference strings. If we had extra time, or sometimes in class, I'll show you some additional examples. So these are 2 slides or a few slides showing some of those other examples. I don't think we'll work these together now. But I just made up a longer reference string, and you've seen FIFO and opt, so you could, if you wanted, you could try that out with those 2 algorithms. I've got a couple of slides here if you wanted to try that on the slides, and if we work these together, we'd be filling these in based on that. Continuing to sort of look for what makes a good page replacement algorithm, it seems like we're done looking for a good page replacement algorithm. We've got this algorithm suspiciously named opt. It's provably optimal with respect to reducing page faults. So why don't we just implement that and be done? And the problem, as you probably could tell, is it's got the same problem as our optimal CPU scheduler, at least in terms of waiting time. This algorithm requires knowledge of the future. To run the sort of hand simulations of opt, we had to look ahead to what the process was going to reference in the future. And the OS doesn't normally know that. It's the process that chooses what pages it needs to access. And the OS can't normally know what that's going to be without letting the process try to access it. So we have an optimal algorithm, but one that's impossible to implement. So the next thing we're going to talk about is, well, what can we do? What did we learn from opt? And we'll discuss that, but I'll save that for the next lecture. Let's stop this one right about here.